Okay, so how did we do with this homework? I heard lots of comments.
50%.
50%. All right, so let's just let's go through it. Let's go through it. I'm not gonna check it off. No, I should, I guess, but I would prefer you'd be able to hold on to it so you could use it on tonight's. What page was it? I'm sorry.
128, 129.
Okay, but we did A.
You had to do
Correct.
B and C.
So, okay. Let's work through B, C, and D. And yeah, we didn't actually do that. All right. So rather than me writing on top of the sheet, I'm just going to go off of this. So this says the table below shows the time and days of spring after March 21st. And the snowpack. So yesterday we talked about it. It was an increasing snowpack. Now it's going to be a decreasing. So I'm going to put in a graph, and I'm going to do the quadrant graph. All right. So, yeah. Oh, hey. Thank
Hi.
you. Not here.
Not here?
Yeah.
Okay, thank you.
All right, so I have the numbers off. Is there a way I can? Let's see. Just trying to think how I can increase this graph. That goes up, down.
Wait, that magnifying glass thing.
So. Black. This.
No, the black box. The box surrounding the.
Yeah.
Oh, like this.
Yeah,
No.
but try it without the.
How did it go? Or not?
Wait, now click the arrow.
We're fine. We're fine. We're fine. We'll make it work. All right. So, this is snowpack. So they gave us some data. We had time and days, and when we had snow. Okay, so 0, 156. That's like deep snow when spring started. So it's starting at 0, and then it goes 10, 140,
20, 120,
20 and 120,
30, 110,
30 and 110, thank you,
40, 95,
40 and 95,
50, 75.
and then 50 and 75. So again, we talked about these saying that we are going to plot the data. Being we're working with linear equations, we'll get a linear equation. So time and days is down here. So it looks like from 0 to 50 days. So I have 0. Let's see if I go 10, 20, 30, 40, 50. That's not really enough. Maybe I can go 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. That'll work. So count by 5s. 15, 20, 25, 30, bless you, 35, 40, 45, and 50. So that should be enough there. What about the snow? I have a total of 156. That's the most. Bless you. So these are this is the snow. So should I count by 1s? Should I count by 10s, 20s, 50s?
20s.
20s? 20s might work. I mean, it goes up to that. So I get 0 here, 20, 40, 60, 80, 100, 120, 140, 160, 180, 200. We don't necessarily need it all, but I think 20s is a good way to count on that. Now, one thing, and science does this incorrectly very often. science doesn't always start at 0, 0. Okay, and they might have a little squiggly line. And it's just, it's, the math people make fun of the science people, the science make fun of the math. Everyone loves each other though. So let's plot our information that we do know. So at 0 days, we're at 156. So perhaps here, at 10 days, we are at 140. At 20 days, we are at 120. At 30 days, we're at 110. At 40 days at 95. At 50, I'm at 75. So it kind of appears it's going to make a straight line. So with this information, let's see if this is going to work for us. Got that? Okay. So we need to start figuring out how we could make a nice linear equation. Y equals mx plus b. We want to get to this. Okay? Is there information that I know up there that I can use?
Yes.
Yeah. So and I forget, let's see. The independent variable is the x-axis. So these are the independent, which is days, and this is the dependent on the y-axis. Okay? The y-axis, the x-axis has an effect on the y-axis. Okay, so the days, this is a decreasing slope because the snow is melting. Day 0 isn't the start of time. Day 0 happens to start on March 21st, 2010. So do I know what my y-intercept is? Yeah.
0, 156.
Yeah, so 0, 156, I know that 156 is my b value, excuse me, which I can plug into this. So then I have to figure out another point. So what did I talk about yesterday that might have been good? So if we're using this point right here as one of them, should I use the one right next to it? No. Use something further away that looks like it appears to be on the line. So this looks like it'll appear on the line. I guess we could use that one if we wanted to, but it's up to you. So that's our last piece of data. So our other piece of data is 50, 75. So we don't know what the slope is at this point, so we can go ahead and find it. The slope equation is this. And I'll call that x1, y1, and call that x2 and y2. Is that all right? We'll plug it in. So I get 75 minus 156. If you have a calculator, it would be great if you got it out. And then I'm going to go 50 minus 0. So 75 minus 156 is? Negative 81. Negative 81 over 50. I can't reduce that. If I'm decreasing it with our slope, does it make sense to have a slope that's negative? Yeah. So what does negative 81 over 50 say about the slope in the context of this problem? There you go. The snowpack is decreasing 81 inches every 50 days. Okay? So we can plug this back into our equation. So here's our equation we knew. We already knew b was this. So I have y equals negative 81 over 50 x plus 156. So let's answer the questions a little bit. Plot the points we've done. Write the equation. What are the 2 points we'll use? We chose those two. The reason we chose the one is it falls right on the y-axis, which is great. You won't always get where it falls on the y-axis, but we might as well use it. Yeah.
So if you choose a different point, like the 40, 95, would it still equal negative 81?
You're going to be really close, but that's also something that I would realize during the test. you know, if you were to pick two different points, I got negative 81 over 50, but you might got like negative 77 over 51 or something like that. But it should be a little bit off because it's not 100% accurate. You're making a prediction based on the model that you have.
Wait, so as long as it's like somewhere around there, it's fine, right?
Yeah.
Okay.
If you pick two different points, you're going to be off just a little bit. And that's okay. As a grader, I know that, and I know that's how it should work. All right. Does the scatter plot have positive or negative correlation? Does it have positive or negative? It has negative correlation. How do we know it's negative? What stands out to be negative up there? The slope. So if the slope is negative, you have negative correlation. If it's positive, you have positive correlation. Okay? If it's just all over the place, you don't have any type of correlation. What is the slope? We said negative 81 over 50 as far as what we chose. What does this mean in the context of the problem? We just stated it. We will be losing 81 inches of snow or snowpack for every 50 days. If you made it a decimal, that should work as well. Okay, and that's fine.
Wait, off topic. Well, what's the difference between snow and snowpack?
Well, so the snow when it falls, the weight of it is going to compress down, and snowpack is the compressed down version. All right. What are the coordinates of the y-intercept? Well, we said it is 0, 1, 56. And what does that mean in the context of this problem? Yeah.
On March 21st, there's 156 inches of snow.
There you go. On March 21st, there's 156 inches of snowpack. Was there more snowpack than that earlier in the year? Well, there could have been. But we're just starting. We had to start at some point. Use your equation to find the snowpack on the peak 70 days after spring. Okay? So which variable represents days? X or Y? X. So if I wanted to figure out after 70 days, how much snow do we have? If I plug 70 in there, and I need you to help me on a calculator. So negative 81 divided by 50, it's going to give you some numeric value. Whatever that is, multiply it times 70.
Negative 113.4.
So that would, and then add negative 113.4 to 156.
42.6.
Okay, so let's double check it. So Ram said yes, and there someone said it was wrong. Negative 81 divided by 50, enter. Still with me? Times 70, enter. Plus 156, enter. 44? Joe? Is anyone else doing this problem?
Still got 42.6.
Okay.
I got 42.6.
42.6. Good. And I also got 42.6. So there's 42.6 inches of snowpack left after 70 days. Think about what this line's doing. Is this line going to continue? Right? I mean, our graph's kind of goofy. Thanks, Bob. Okay. So our graph continues on and on forever. So at 70 days after we started our observations, we get down to 42.6. Okay, so that's what that graph is doing. Now, at the last question, how many days into spring will the snowpack on Wyoming Peak get down to 0 inches? So think about what this line's doing. That's 0 inches. That means we have no snowpack. So what does the x-intercept represent in the context of this problem? At what day is there now 0 inches of snow? Okay. Do you need to go? I don't know what that was. Okay. So, how would we find this value here? Using my equation. Plug it in where? For y. Okay? So plug it in for y. So I'm going to get 0 equals negative 81 over 50 x plus 156. So let's solve for x. Subtract 156. Okay? Help me out. How do I solve this problem right here? Okay, good.
You divide by negative 81.
Okay, I'll divide, so I'll multiply by 50 and I'll divide by negative 81. And what this is going to tell me is, if I do that math, it comes out to roughly 96.3. Okay, so if our model is correct, and it's something that we're going to make a prediction off of, 96.3 days after March 21st. So you're talking over 3 months past March. So you have March 21st, April 21st, May 21st, June 21st. So sometime in late June, if our model is correct, we should not have any more snow on the mountain. It's all melted. Does that seem like a true type of thing that could happen here in the state of Colorado? I mean, I know that I've seen the mountains in our summertime, and some of our higher peaks still have snow on them, right? Or if you got driven up to the mountains, you might have gone on hikes, and you might have gotten into an area that the sun is not directly shining on, and you might have come across snow. You might have come across glaciers. I mean, this is all things that do work. We do have a small glacier field here. So this is a pretty real depiction of how this might work. So that's letter B. Letter C, let's look at this. It says the table shows the population of Carbondale, Colorado for the given years. Carbondale, Colorado. Okay, so let's bring up our quadrant graph. I don't want the numbers on there. Okay, the year is say we have 1950, 1960, 1970, 1980, 1990, 2000. Okay, so should I start here being 0? And if I do, what does 0 represent on our table?
You can start on 0, but you would have to count by tens.
Or there'd be no
So let's think about this. 1950, 1960, 1970, 1980, 1990, and 2000. Get up there. There's 500 people here, 800 people here, 1,100, 1,500, 1,600, and 1,900. Okay. I do that right?
Yeah.
Okay. So let's think. No matter what we do on our x, will each little square be the same amount? Yeah? So our starting point is 1950. So I guess I could write 1950 right here, but that's a really bad representation. So let's put this at year 0. Okay? At year 0, we have 500 people. Okay? How far is this from here and here normally? 10 years. So let's make this at 10 years. And then make this at 20. Then make this at, and 50. So if I were to say at 20, well, that represents the year 1970. Okay, so I'm going 50. So maybe I'll count by 5. So 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. And that represents the years. And then our population goes from 500 to 900, or 1900. I don't think counting by 500s would be great, because it'd be 500, 1,000, 1,500, 2,000. We're already there, and that doesn't really. 200s? That might be good. So you might be right, though. Let's figure it out. So 0 people, and then we have 200, 400, 600, 800, 1,000. Does it seem like it might go okay? That's 1,200. That's 1,400. 1,600. 1,800. 2,000. You think that was a good thing to count by? Are they all evenly spaced?
Yeah.
Absolutely. Okay, so at 0, 500, that's about here as far as our data goes. Okay, what did 0 represent in our problem as far as the x goes? The year 1950. And then 10 years after the fact, we are at 800 people. 10 years after that, 1970, we are at 1,100 people. 30, I'm at 1,500. 40, I'm at 1,600. And 50 years after the fact, I'm at 1,900. Does it appear to be somewhat linear? Are there some that are a little goofy?
Yeah.
All right, so it appears to be linear. I don't know, let's put our line up there. How's that look? I like it. Everyone see the big red line? No, I'm missing it. All right.
It's too thin.
It might be too thin. All right, so item 1. Would I know where it crosses the y-axis in the context of this problem?
Yeah.
Yes. 0, 500. Now, what does this help me with? It helps me with slope, absolutely. I mean, that's the y-intercept. This is my b value right here. So I'm already set with this equation so far. I need to figure out slope. Well, I made my line too thick. I can't really see which 2 points are real good. So perhaps I'll say this one and this one. How about that? So that's at 1990 and at 1600.
Oh, yeah, but you do 40 since you
Well, we're going to put a 40 in place of the 1990, right? These are the same. Do you agree? So let's figure out our slope. Let's see, on this problem, our independent variable is the year. And our dependent variable is the population. Okay? I'm going to go ahead and find my slope. I know this is my slope equation. I'll label that x1, y1. Label that x2, y2.
Let's still come out as the same answer.
1600 minus 500. 40, 0. That's 1100 over 40. I can reduce that to 110 over 4. I can reduce that to 2 goes into both, right? 55 over 2. That's our slope.
The slope of 30.
You might have chosen 2 different points. But that could happen. I think you're right though, Ram.
I did some.
Did you choose my two points?
I chose 2 different points. I
2 different
chose
points.
the
But
first
but
two.
you see, but you know what? 55 divided by 2. You probably had 60 divided by 2.
I had 300 divided by 10.
300 divided by 10 is 30. Yeah. So 300 divided by 10 is 30. 55 divided by 2 is, you said 27. Yeah, 27.5. So that's pretty close, right? So in the context of this problem, what does the slope mean?
55 people move in for every 2 years.
Yeah, as far as the slope that I chose, 55 people would move in to our town every 2 years. You had 30, which is the same thing as 30 over 1. So yours would have been in context saying 30 people move in every 1 year, something like that. But that's how that would work in the context of the problem. Positive or negative correlation? Positive. We know that. We can look at the slope. If the slope's positive, then it means it's positive correlation. What are the coordinates of the y-intercept? We have 0 at 500. What does that mean? That means that when we started counting in 1950, we had 500 people already living there. Okay? And then, what will the population of Carbondale be by 2020? Okay, so let's figure out when 2020 would exist up here. Yeah. So 2020, so 2010 is 60, 2020 is 70. So this is at a 70 mark. Where does the 70 plug into our, I guess I should make my linear equation. 55 over 2x. Plus, there's an x there, plus 500. And then where does that 70 go in? It goes into x. So I get 55 over 2 times 70 plus 500. So help me out. I don't know. 2425?
Yep.
So 70 years after the fact, I'm going to have 2,425 people living in my town. Okay? Is this to say that everything in this town's going to remain the same? You never know. You could have, some industry that decides to move in town, and all of a sudden your population booms, and it's no longer a linear thing. But as far as this goes, that's how a prediction could take place. And then, when will, according to our model, in which year did the population reach 1,500? It happened in 1980. Good. Okay, now let's take that. Okay, so we have this right here seems to answer our question. Agree? But I want you to be real careful with this type of thing. I could also take that 1,500, plug it in for y on my equation. Now let's see if we're off a little bit. 55 over 2 times x plus 500, right? So I'm using my linear equation here. I'm plugging in 1,500. So if I subtract 500, this becomes 1,000. Multiply by 2, so I get 2,000 equals 55x. So if I go 2,000 divided by 55, what do I get? 36.36. So at 36 years after 1950, I add 36 years to get to here. 36 years, that's like 1986. Our data shows this, right? The data gave me the answer. But if I had my answer here, this is my linear model. Our linear model gives us a slightly different answer than what this data showed. And that's margin of error. actual versus predicted times 100. Okay? Are there times you could predict something taking place? I mean, 1980, there's 1,500 people. We showed that in 1986 we'd be at 1,500 people. Are we wrong?
By a little bit.
But there's a percent error is what's taking place. Do you agree? There's a certain error. I mean, if someone were to say to you going, hey, when did your town get to 1,980 people? Or when did you guys get to 1,500? 1980. And then somebody said, well, I have this linear model, so is that 1986 is when you actually hit it. Who's right and who's wrong?
Well, both of you are.
Both of you are correct. One of you is looking just at the data. 1980, so that's 1, 2, that's a fourth part over 1, 2. So this piece of data right here, or no, I guess it would have been this one over here. So you know how our lines, we have our data, I mean, a lot of times your data will look like this. You'll have a whole bunch of data that you put on a line, not just 6 pieces of data. And so then you show a line of best fit like that. And sometimes this right here might be the answer that you think you're looking for, but because of your line of best fit, your equation you created, and there's tools we have in math that allow us, especially on the calculator, that allow us to tell how correct the graph is going to be. The more data you have, the better linear model or any type of model you could have. Just a couple of things. It'd be like me, if I were to take a coin, if I pull a quarter out of my pocket, which I don't have one in my pocket right now, but if I flipped it and got heads, that's one time getting heads. And I said, okay, who wants, everyone want to, you think it's going to be heads versus tails, and someone says, oh, well, it's already heads, so tails got to come up. The coin doesn't remember me flipping it. So I could flip a coin 10 times, and all 10 times get heads. And of those 10 times getting heads, it's like, oh, wow, that's kind of weird. Uh-huh. But it should happen. Does it have to happen? No. I could get 5 and 5 of each. I could get more tails than heads. I could get 1 heads, 9 tails. It doesn't matter. But it's the model that you're using to predict that you might have to. There's a margin of error that does take place. Yes, our data did show that in 1980 we had 1,500 people. That was what our data showed. We created a linear equation by choosing 2 points. And the reason I chose 2 points is 2 points define a line. But think about this. If I were to, let me just put a dot here. Let's say I have this dot here. Let's say I have a dot here. Let's say I have a dot here, and I have a dot here. If I pick this dot and this dot, I'm getting the linear equation we should have, or that we're using right now. If I choose this dot and this dot, am I getting a slightly different look?
Yes.
Yeah, this is what this linear equation would look like. What about this dot and this dot? Is it a little different line? Yeah, it goes this way. Actually, it looks like it has a negative slope. What about this one and this one? Oh my gosh, that's undefined slope. They're vertical to each other. So what's the right way of doing it? Again, you look at it, you say, okay, here's my line of best fit. This piece of data way over here and this piece of data way over here seem to be on that line that we are choosing. Rom had a different answer than us than I had done because he said he picked 2 different points than me. Is Rom's answer wrong? No. So in Rom's scenario here, would he have gotten closer to the 1980? Maybe. Who's right? Both. Why? Because we're making a prediction off of observations using a linear equation.
So does that mean that any predictions about the future are always off by a lot?
Well, depends what a lot is.
I mean,
For us.
I mean, 6 years is a lot.
I mean, a lot to a kid is not as much for an adult. Like your ice cream falls off your ice cream cone and hits the pavement. Your world's just done. What does Dad do? I'll go buy a new one. Here, have mine. I'll eat yours. You off the street, sure. My immunity will build. I'm okay. I mean, so what is big, what is small, what is something that is acceptable and what's not acceptable. There's all kinds of things that a lot of math will go in and talk about. All right, this last problem I actually want to do on the graphing calculator. I didn't ask you to do it last night. Let's pull up the graphing calculator. If you have a graphing calculator, get it out. If you need a graphing calculator, I have a few you can borrow, starting with this one. Anyone need one up here? If you need one, come over to this cabinet and grab one of these white ones. Grab one of the white ones off the charger. I don't know, you were getting ready to sleep almost. All right. If you have that graphing calculator, let's do this. First thing, let's find the on button. That's a disclaimer I have to make because guess what? I'd get 3/4 of the way through a problem there and that cabinet's open. Get 3/4 of the way through a problem and you just don't get, oh, how do you turn it on? So the on button is down here in this lower corner. Yes?
Yes.
All right. I'm not going to have enough time. So no way, shape, or form by you seeing this done one time does it make you a master of doing it. Agreed? All right. Hit the clear button if there's anything there. A few things we need to do. You see this button that says second? Click that, and then click Y equals. So click second, Y equals. We're going to turn our stat plot on, so hit number 1. If it looks like this, let's not worry about color. It's not the most amazing thing. Hit enter, it's going to move it over. So that's what you want your graph to start looking like. I don't care if you use blue, red, green, or if yours is just the black and gray. Doesn't matter. Okay? So by me doing this, I've turned my plot 1 on. It should be like that. We're going to have it as a scatter plot. We don't want to do a connected bar graph, box and whiskers modified, or a step. We want L1 and L2 to be there, and then you can pick. Do you want a square, a plus, a dot, or a smaller dot as your mark? I don't care. Use your arrow keys and enter to change it. I don't care about the color. I'm not worried about it. Yours doesn't have color.
Wait, which type of graph does it have to be?
The very first one, the dotted one.
What's a cat and whiskers?
We'll worry about that when you get to another math class.
I hated that
It's
one.
the way to look at your averages and inside averages and your max and mins. All right, are we all at least about here? If not, I'm moving on. All right, now I'm going to go second mode, which is mode is right next to second. So second mode. Okay? Now you're going to hit stat. This button right here, see where my cursor is? Stat. Okay, hit number 1. And we are going to put our data in. Okay, list 1 on problem D is going to be 2, 4, 6, 8, 10, and 12. Just use your number keys. You can use the up, down arrow keys. If you made an error, you can hit enter. And then under list 2, and you can just copy this off mine, these are the values you're plugging in. So this is coming off of problem D. Okay? Seem okay so far? Okay, so you remember when we turned our stat on? Remember that? This means that we can go ahead and see what our data is going to look like on our graph. So the first thing I want you to do is this, because these calculators are used by other people, and yours might have other things. See this y equals up here, where my cursor is? Hit y equals. Let's make sure there's nothing there. If there's something there, just hit clear, which is under the arrow keys. You don't want any equations in here. But yours might look like mine, where it has plot 1 is highlighted and darkened. Okay, so if you plug that data in, you can do this. Zoom, and then find zoom stat, which is number 9 on mine. And lo and behold, it should look something like that.
Mine's got a
Mine
picture.
just has a dot.
Mine's got a picture on it.
Why is it? Show me it.
Let me see.
I need to see this. Wait, that's a picture, that's a graph, and then you have 2 lines. You have to clear the other at y equals mx plus b. Wait, how do you clear this?
Zoom, very top middle button. This is stat.
Are we gonna have to remember how to do this?
We're just going to walk through it. I would probably give you a worksheet. Oh, you can now see, you chose yellow dots, so they're real faint.
Oh,
See them?
yeah.
All right. Now, here's where the calculator gets cool. All right, just by looking at this. Linear regression, so it's a single line. Positive or negative correlation?
Negative.
Negative. It looks like a negative slope. Still with me?
Yeah.
All right. Now, put your calculators down because I'm not going to be able to talk you through this. I just want to show you what this will do. Okay? So with here, I can hit, I gotta remember, stat, calculate. I want the linear regression, number 4. I'm going to use list 1, list 2. Calculate it. So my equation, y equals negative 105.7 x plus 223. If I go into y equals, I can do this. Bars, stat, equation, 1, graph.
Oh, that's real.
Oh.
That's cool.
Cool.
Wait, how'd you do that again?
It's too many steps for me.
Are
I'm
we
not,
doing tomorrow?
okay?
Wait, how do you clear this data?
I'm not worried. We'll take care of that a different time. All right, so few things that this graph will do. Okay, so this was, I worked all summer to save money for my first semester of college, and I spent a little each week. These are the records I kept. So time in weeks is our x variable. Money in my account is my y variable. So if I did this, watch this. Second, calculate. So I want to know after 7 weeks. After 7 weeks. Boom.
Wow.
After 7 weeks, this is my information. After 7 weeks, I have $1,283 left. So this did the automatic thing for you. If you wanted to figure out where it's going to get to 0, you would have to zoom out on your graph a little bit. So you'd have to zoom out, enter, and that's going to do that with you.
Zooms out a lot.
Yeah, I mean, it just depends. So this is where it's going to be there. So what I'd have to do, if I wanted to figure out where that happens, that is the line. I'm going to go into y equals. My y2, I'm going to go y equals 0. Graph. Graph. Notice the red line now. Watch this now. Let's see. I want to go second, calculate the intersection of my 2 linear equations. And it's going to tell me after 19.1 weeks, I'll have no money left if I continue to spend that way. Okay? So, what is the slope in the context of our problem? The slope is, I don't even know what our slope was. What did we say was on our linear equation? It was y equals. So I spend $105.71 per week. That's what basically this linear equation says. Okay? So I would like you to have a start on, worksheet. If you have a calculator, great. If you don't, well, just start it. See how you can get page 131 through 1. And this is not going to be due. Again, it's not going to be due because everyone doesn't have a calculator. 2, it's a very new concept. So we're going to do this through 133. And we're going to use the graphing calculator quite a bit. So if you could start it, you might not need the graphing calculator. Make sure you turn the calculators off that you borrow. Put them in back there correctly. I can't dismiss you until I have all 10 of them back, okay?
You said it's not due?
It is not going to be due. We'll start it and we will finish it in class, and then I'll make sure everyone gets points for it. Cool?